in this last discrete distribution that we're going to look at, we're going to take a look at something called a Poisson distribution. The Poisson distribution, essentially, the only parameter or the only variable you need to know is the number of successes in a fixed interval. So you don't need to know what the probability of success is, and you don't even need to know how many trials you're doing, right? So this is given by a variable called lambda. And so, for instance, an example to where you would use the Poisson distribution is, let's say, on average in a week, a machine breaks down 3 times, or maybe each year there are going to be 16 students that earn full scholarships to UMBC on average, okay, at Hartford Community College. So these are the ideas of a Poisson distribution. It's not really used too often. Most of the time, we would try to use a binomial distribution or another type, but the Poisson distribution can be utilized to gauge probabilities based on these very loose parameters. It's actually one of the easiest types of distributions to use. And so 3 formulas, 2 of which are very easy, 1 of which is a little ugly, but not too terrible. So the expected value is going to be mu, which is going to be lambda. And lambda is going to be the number of successes in that fixed interval. So that's pretty easy, all right? If you take the square root of lambda, that's the standard deviation. So that's easy too. Not so easy is this ugly looking formula for p of x, lambda to the x e to the minus lambda over x factorial. X is the number of successes. We know what a factorial is. We talked about that a little bit earlier. E is going to be a calculator button. All right, now E is really just the natural exponential base, but for our purposes, we're just going to utilize it as a calculator button in this course. So let's take a look at some example problems. This is really easy stuff. It's known that in a computer lab, the average number of computer viruses in a lab per month is 7. So the only number given here is lambda, which is 7. So we know that lambda is 7. And for part A, this is really easy. What are the mean and standard deviation? Well, we know that mu is lambda. And we know that sigma is the square root of lambda. All right, we're going to shove that in our calculator. Square root of lambda, square root of 7, is going to be 2.645 or 2.646. So that's easy. All right, easy enough. Probably the easiest formulas we've looked at in a little while. What's the probability of observing exactly 6 viruses? Right? So we want to know P of 6 equals what? Now we know our formula is lambda to the x e to the minus lambda over x factorial. And we know that x is 6, and we know that lambda is 7. All right, so let's just substitute back in. So this is going to be 7 to the 6th e to the minus 7 over 6 factorial. And then, of course, the question is, well, how do I put that in my calculator? Because I'm not going to be able to do that in my head. So in our calculator, we are going to do 7 raised to the 6th, and we're going to kind of hit this right arrow to get out of there. We're going to hit second and ln, and that's going to bring up this e function. Okay, so second e to the minus 7. Okay. We're going to back out of that, and we're going to divide by 6 factorial. Now, 6 factorial, we just hit 6, we hit math, and we're going to go to prob. And notice the 4th one down, at least on this calculator, is the factorial. So there we go. And that's how you put it in there. If you missed it, just watch the video a few more times and practice it until you get it ingrained in your head. 0.149 is your probability. Okay, really nice and easy. Okay, so this is 0.149 or 14.9%. Right? So it's not completely out of the question that there could be 6 viruses in the lab in a month, given that 7 is the average. Finally, what is the probability of 5 or 6? So just like we did before, we're going to take P of 5, and we're going to add that to P of 6. And we already know P of 6 from before. Remember, it's 0.149. So for us, all we have to do is figure out P of 5. And our formula, well, we're just going to switch out all the 6s with 5s. So that's going to be 7 to the 5th e to the minus 7 divided by 5 factorial. And if you remember anything from the videos, one of the cool things is we can use that trick. Just hit second enter, and let's just switch all the 6s with 5s and be done with this problem. And we do have to add it together. That's not a big deal. All right, so we switch that to a 5, and it's going to be 0.4 or 128. Right, and then finally for our, we should say P of 5 plus P of 6, which is 0.149 plus 0.128, and that's going to be 0.277, I think. But of course, we want to go back to the ultimate authority, and 0.277 or 27.7%. Right. So a really easy problem. All right. Hopefully that makes sense to you all. You might want to pause the video here and just try this one for yourself, the exact same type of problem that we just looked at. All right. So a warehouse estimates that approximately 15 items are recalled each week. Mean and standard deviation exactly 13, and then 16 or 17. Right? So maybe pause the video and practice this, and then start it up again after you've practiced. Hopefully you went back and practiced. If not, shame on you. We know that in this problem, lambda is equal to 15. All right, and why do we know this? Because there's 15 items recalled. That means that for letter A, lambda, which is mu, is equal to 15. And the standard deviation, which we said was the square root of lambda, is the square root of 15. And that's going to be like 3.9 or 3.8 something. So square root of 15, 3.87 to 3.873. All right. So that's the mean and deviation of this. So that means we have a standard deviation of about 4 recalls each week. All right. So an outlier, if we multiply 3 times 4 is 12. So if we got 15 minus 12 would be 3 or less, or 15 plus 12, 27 or more. All right. So those are just like the benchmarks for the outliers. All right. And we probably remember that from the other videos. All right. Probability of 13. Remember our formula. Lambda to the x, e to the minus lambda over x factorial. Well, x in this case is 13, and we know that lambda is 15. So that's going to be 15 to the 13th, e to the minus 15 divided by 13 factorial. And let's just shove it into our calculators. Now let's just start this one over again because we don't want to reuse it. So it's lambda, which is 15 raised to the 13. Remember that trick, you hit second e to the minus lambda, which is minus 15, and then we're going to divide that by 13 factorial. 13 math, go over to PRB, it's fourth one down. All right, and 0.090956, so 096 about the probability for that. Right. And then finally, what's the probability of 16 or 17 recalls? All right, so we're going to find P of 16, we're going to find P of 17, and we're just going to add those together because it's an OR problem. That's going to be 15 to the 16th, e to the minus 15 divided by 16 factorial. And this is going to be 15 to the 16th, e to the minus 15, excuse me, not 16, 17 divided by 17 factorial. Right, so let's just figure those out real quick. The good news is we've already programmed them in our calculator. So we can just hit second enter, and we can do that trick that we've seen a time or two. So 15 to the 16th, e to the minus 15 over 16 fact. All right, and then we're going to hit second enter. Might as well just do 17 while we're here. And 0.096 and 0.85. All right, so 0.96.085, and then we're just going to add those together to get 0.181. Of course, I'm going to check the calculator because I don't trust myself. So we're going to have 0.096 plus 0.085, and we do indeed get 0.181. All right, so hopefully this gives you an overview as to what the Poisson distribution is and how to use it. And hopefully you understand that it's not too scary. All right. In our very last video, we just have one more problem, very similar to the other two, except we're going to extend it a little bit with the concepts.